Hi, this is Kevin Farlee. I'm here to talk about HADR and SQL Server. HADR can be a pretty complex subject area. The basic ideas are pretty simple, but there's a lot of moving pieces to think about when you're protecting yourself. You have to know what are the threats you're protecting yourself about, as well as what are the assets you have to keep yourselves away from those threats. So we're going to talk about putting all those puzzle pieces together, a little bit about planning for the future. Little plug for PASS. PASS has a lot of different things to offer, so please explore what's around. PASS.org has some free resources. PASS Marathon, local user groups. If you have a chance, if you haven't connected with your local user groups, it's a great way to connect with local SQL people around the area. Make connections. It's a great thing to do. SQL Saturdays are great one-day local training events as well. A little bit more about me. I'm a principal program manager in the SQL Server team. Been with Microsoft about 15 years, in the industry a lot longer than that. So I've focused on storage management and database software this whole time. So for the rest of the time, this is what we're going to be talking about. We're going to talk about what is HADR to make sure that we have a clear understanding of what is high availability and disaster recovery. What are the requirements you're trying to mitigate? So what are the threats you're trying to mitigate, and all that. Talk about HA and DR features in SQL and how it's a progression from over the versions of SQL. The features have built upon each other to give us the rich set of solutions that we have today. We'll talk a bit about the new features that are available in SQL Server for HA. A discussion of what to use and when, so scenarios and solutions. So with this scenario, what solution would you choose? And just a little bit about platform choices. So are you going to deploy within Azure? That gives you some unique capabilities. Or are you going to deploy on-prem, which gives you control? So there's a lot of different trade-offs. Those are just a couple simplistic pieces. So that's what we're going to be talking about. So what is this HADR thing? So what have we been talking about here? So what is this HADR thing that we've been talking about? How can we get a handle on it? So disaster recovery, HA, high availability and disaster recovery. Starting with disaster recovery, it's recovering from an event which takes a large part of the infrastructure offline, typically a site or regional outage. So you lose connectivity to a site, or there's a regional disaster of some kind that takes that whole site offline. So that's what we're thinking about when we think about disaster recovery. It's not just a machine crashing, although that's a disaster in its own, but DR contemplates an entire site going away. Sort of like that. So when we think about disaster recovery, you assume that the primary site at least is not accessible for some extended period. This isn't just a brief outage, because the things you're going to do to recover from a disaster, do a disaster recovery, are major rebuilding, and you don't want to do that for just a slight blip. The solution would take longer than the problem. Communications may not be possible. So it may be that there's just no way to communicate with the staff or the machines in your remote location. They may be completely offline. You have to rely entirely on resources, both people and equipment resources, at a remote location. So if you have your remote site, it has to be able to function completely independently of the staff and the resources at your primary site. Usually getting online and available is more important than not losing any data. That's not to say that it's okay to lose data ever. It's not. But if you have to choose between losing a small amount of data and losing your business for an extended period of time, days or weeks, you're going to pick getting back online as quickly as possible, because that's also typically lost business. So the highest priority is getting back online and available as quickly as possible. High availability, on the other hand, is a different problem set. People kind of lump HADR together, but they're really distinct problem sets. High availability is maintaining the availability of a service or system with an absolute minimum, ideally zero, downtime for any reason. It's typically represented as a percentage of the possible uptime. So 99.99% would be 4 nines, 5 nines, 6 nines. Obviously, you get up into larger number of nines, you're talking about minutes per year, seconds per year, and that gets to be a pretty stringent requirement. It's possible, it's achievable, but as with all things, for that benefit, you're going to have costs involved. So with high availability, any outage for maintenance, upgrade, failure, planned or unplanned, detracts from the HA goal. So all those things that happen, maintenance happens, upgrades happen, planned or unplanned issues happen, and all of those are what you're protecting against with HA. So you're designing a system that will be resilient and not interrupt your business even when you're doing maintenance, even when you're doing upgrades, etc. So that's what we're talking about HA. It's continuous. So sometimes HA is viewed in a chart like this. So this is a chart that I found up online, and this is a week's worth of time. So you have a block for each hour, and it has whether it's completely up for that entire period, down for 10 minutes or less, or down for 10 or more minutes of downtime. And you can see this place has some extended outages, 10 minutes or more. This is not what you would want to see. It's not catastrophic, but for some businesses, this would be a major problem. But this is just a way to think about what we're considering when we think about high availability. So in high availability, we're protecting against anything that prevents an application from accessing the data it needs. So from the database perspective, there's more around HA than just the database, but from the database perspective, we're protecting against anything that prevents your applications from accessing the data it needs. The applications by themselves don't typically do a lot without data. So you can have your application up and running. If it can't access the database, it's not going to accomplish a lot. Assume the site and facilities are not impacted. So for HA, we're not talking about disasters. We're talking about the site and facilities are all available up online. So that's not the problem set we're solving with HA. Typically implemented by locally redundant equipment. So clusters, availability groups, etc., where you have more than one of each piece of equipment. And so you can do a fast failover. This is how we survive things like upgrades and maintenance without extended downtime. You do a very fast failover to an alternate set of equipment while your original primary is upgraded and failed back. So that's called a rolling upgrade. Outages typically measured in seconds or minutes. The two key metrics, both for high availability and DR, RPO, recovery point objective. That means when you recover, how close did you get to the point at which things went down? So did you lose any data? So the point when you recover, the point you recover to, is that the same as the point that things were at when the lights went out? Or is there a gap where you had to go to the last backup? That's a DR scenario. Recovery time objective is related, but that has to do with how long does it take to get back up and fully operational. So from the time whatever happened, so it went offline, you started the failover for a rolling upgrade, the site went off the map, whatever it was, how long does it take to get from that time to the time when everything's back up and running and you can take a breath? So that's RTO. High availability should not result in any data loss. So you're looking at an RPO of 0 here. So now we're going to start an overview or history of HADR features in SQL. So we're going to talk briefly about which features came along when, and then we'll flip to kind of looking at how some of the features build on each other and complement each other. So starting with SQL Server 2000, as before, we had failover clustering added. Okay. Log shipping. Backup and restore actually belongs before this. It's kind of dawn of time thing. SQL Server 4.2, way back there, had dump and load, which was their version of backup and restore. So that's been there since the very beginning. 2005, that was a 5-year release cycle. We had time to get a lot of cool features in. Database mirroring was added in that time frame. Database snapshots. Checksum IO validation and read retry. So what this means is if when we read a page, we validate the checksum of the page, and if it doesn't validate correctly, we retry the read to see if maybe it was just a dirty read, and sometimes that will clean things up for us. Mirrored backups and restore media checks. So this is where you can, a mirrored backup is when you do one database backup and send it to 2 separate sets of media. And then you can have also restore database with verify the media checks that make sure that the media is clean. Fast recovery, it's a difference in how we do database recovery when we're bringing the database online. We reordered some things to make it faster. There's been some very recent changes in that area that make things way faster even than that. And online restores. Moving to 2008, we had write ahead on the incoming log stream compression. So we compress the log stream to make it much more condensed. Automatic recovery of corrupted pages. SQL Server 2012 came along with always-on availability groups. So that was a big change in the HADR landscape. Multi-subnet clusters. So you can have a failover cluster that crossed subnets, which opens up the ability to do things like stretch clusters. So you have one single failover cluster that spans multiple sites. Obviously, you're doing storage replication in that case, but the networking is really hard if you can't span subnets. Flexible failover policy, so more granular in what triggers a failover. 2014, we upgraded the number of secondaries up to 8, so you can now have 8 replicas. Online secondary replicas after quorum loss. So what this means is even if you lose quorum, your secondaries can stay online. You can't do updates because without a quorum you don't know who has what, but you can still access the secondaries and keep at least your reporting and your read access viable, obviously while you scramble to resolve the quorum loss. Cluster shared volumes for failover cluster instances. This is a Windows cluster feature which does sort of the same thing that a SAN replication would do, but within the operating system. So you have multiple separate volumes, and from that you form one logical volume which has both of those underneath it, and you can failover from different machines and have direct access to the data, whichever machine you're in. 2016, availability group for standard edition. So previously you had database mirroring, which was available in all SKUs. To move to availability groups, you had to go for enterprise. We desired to retire database mirroring, although that was probably, who knows when that will actually happen. But one of the steps is giving you a viable solution in standard edition. So this gives you basic availability groups, which have the same surface area pretty much as database mirroring. So you have limited to 2 replicas. There's no read access to the secondary, and there's a few other restrictions, but the mechanics are all availability groups. So when we finally get there to migrate people off of database mirroring, it'll be a simpler landscape. Again, don't panic, that's not coming anytime soon, but that was the motivation behind there. Load balancing of read intent connections. So this is when you have a primary and multiple secondaries that are all enabled for read intent. when you make a connection to the listener for application intent is read, we will round robin across the set of eligible secondaries. So you're not sending all of your read access traffic to the same replica. You can spread the load over a number of different secondaries. So if you have a workload where it's really read intensive, you're doing lots of read accesses, then you can spread that load out over more pieces of hardware, and that increase your performance that way. 3, auto failover replicas. So it's, again, just upping the bar. You have more auto failover targets for your replicas. Distributed transaction support for availability groups. Database level failover detection. And distributed availability groups. We'll go into a lot of detail on how distributed availability groups work in just a second. And direct seeding of availability replicas. This is a really cool feature. We'll talk about it more, but basically the availability group will take care of all the mechanics of seeding the database. So you stand up a new replica or add a database to an availability group. We will take care of doing the work of backing up the database from the primary and restoring it on the secondaries for you just automatically. And log transport performance improvement. So we went through the whole log transport for availability groups and down to the level of how many context switches are there for this packet to get from here to there. Really streamlined that whole pipeline and made a huge improvement in the throughput we can get out of that transport. We found that we were bottlenecked within the engine there, and so we got rid of that. One benchmark that we did on some pretty snappy hardware, admittedly, I saw over 300 megabytes per second of change traffic going over that log transport. So that was a big enhancement. And that was driven by one of our customers that has very stringent performance needs and keeps us on our toes. It's a lot of work, but it's something we really, really value, is having customers that push us hard. SQL Server 2017, of course, was all about choice, support for Linux, and HA support for SQL Server on Linux was a must-have. You can't have a database without HA support as well. So most of the HA functionality is the same on Linux as it is on Windows. There's some differences in the mechanics. So instead of Windows Failover Cluster, you may have Pacemaker or Service Guard or some other Linux native clustering solution doing the orchestration. The basics are all the same. Full distributed transaction control support, coordinator, read scale availability groups. Again, we'll get into those in more detail as well. There's new cluster types. When you're in Linux, there's different cluster types, so you can have integrated, external, or none for cluster types. Required sync-canaries to commit is a new option. I'll get into what that's about and why it makes a difference and why you would or would not want to choose it. SQL Server 2019, we've got a couple new features. Distributed network name support and Azure Shared Disk clusters. So DNN is a technology that came out of the Windows Cluster team. We're adopting it and supporting it. It makes configuration, particularly when you're running on Azure VMs, much simpler, much more streamlined. So it's a good thing. And Azure Shared Disk clusters is a way to leverage the new Azure Shared Disk technology to give you a failover cluster, which to SQL looks like you just have a physically shared disk. Pretty cool. So now we're going to get into looking at the HADR technologies as a progression. So we looked at it through time previously. Now we're going to look at it as how do these features build on each other technically. So first, at the dawn of time, we had backup restore. You have a primary server instance and backup job, backup share. So the backup gets sent to a file, either on the same machine and then copied off, or sent directly to a share on alternate machine. You can send the backup, make a copy of your backup and send it to some cloud provider and have it stored offsite that way. Some people will copy it off to another site within their corporate network. In the old days, they'd put tapes on trucks and move them off to a vault someplace under a mountain. So it's a way of making sure that if you have a disaster where your site burns down, you still have your data protected and you have a way to get to it. One of the features that we've added to SQL is the ability to do backups directly to Azure blobs. So then you can do your backup directly into a blob in the cloud where it's multiply redundant. You can set up the characteristics of that blob to have redundancy built in as well. So then you always have access to those backups. And this is Disaster Recovery 101. This is backup and restore. This is what gives you the ability to get your server back to the state it was in the recent past. So that's would be a full backup periodically and then more frequent transaction log backups to roll your database forward to the point as of the last transaction log backup. So there would be some data loss if you're using this to rebuild your environment, but you can rebuild your environment. It's backup restore is a disaster recovery only. It's not HA by any stretch of the imagination. Copy your data out to a flat file. You can also use storage level snapshots. So there's a Windows facility called volume shadow copy sets, which is a way of doing application aware storage snapshots. So in the SQL's case, if you're using an application that is aware of VSS, the VSS infrastructure calls into applications like SQL and says, okay, we're about to do a snapshot. Make sure what's on disk is consistent at this point. So quiesce the database, quiesce your disk activity, and they do a snapshot of the disk, which is basically instantaneous. If it takes more than 10 seconds, the whole thing times out and rolls back. But you end up with a crash consistent, at least, snapshot in your storage. And then that can be used either on its own to quickly come back to that point in time. You can copy the database files out of that snapshot to other media. There's a lot of different options, but it's a very fast way to get a snapshot of how your data was. It's also very useful for setting up test environments. So you take a snap of your production data, you surface that as a volume, and then you can run lots of tests on it. Backups should be archived off premises. If you're protecting yourself against a disaster, you need to make sure that your backups aren't subject to the same disaster that your primary system is. Different customer site, Azure or other cloud storage what we would suggest. Backups are scheduled, so they need to happen predictably. So you don't have to remember, oh, it's Tuesday, I need to do my backups. It just happens. And your pattern of fulls, differentials, and log backups should be set. There's a lot of patterns for that out there. Tested regularly. A backup doesn't do you any good if it can't be restored from. So make sure that you regularly test the process of grabbing a set of backup files, deciding what point you want to restore your database to, and doing that full restore process. Ideally, that's in the context of a whole DR test. But at least make sure that your backups are viable. I've talked to customers that did full backups infrequently and ran into a case where they couldn't restore their last full backup because it had gotten corrupted on media. They didn't know it. So, test. So the next progression is log shipping. Log shipping makes use of backup and restore. It's just backup and restore, but there's a lot of automation built into it. So with log shipping, what we're doing is On your primary server instance, you have a job that backs up your database. So you do your full backups, but then you have transaction log backups, which are done within the context of a log shipping job. What that means is log shipping job controls doing those log backups, sending them to a backup share someplace. Then there's a second job, the copy job, that copies those log backups to secondary nodes. So here you have 3 different secondary nodes. Each one has a copy job to pull the backups to the secondary nodes. Secondary nodes have jobs running that do restore. So each of them will, when the backup lands on the node, it'll kick off and do the transaction log restore and roll the database forward that much. And in this way, you can have one or more secondary databases, which may be on your same site or it may be on a remote site. This may be part of a disaster recovery where you're protecting against the whole site going down. It's very low overhead, and this is how you can keep your secondaries up to date within the realm of the frequency of your log backups with your primary. And then there's ways to make those databases temporarily readable in between restore jobs so you can get some utilization out of them. So log shipping is built on backup and restore. It's a series of periodic jobs. They back up the database transaction log from the point of the last transaction log backup to the end of the log. And that then allows that region of log to be reclaimed and recycled because the transaction log is a circular structure. You copy that backup file to secondaries, restore the log backup to the secondaries, and then those secondaries can be put in a standby state to give read access. So it's a distinct state where the changes made to bring the database online, rolling back incomplete transactions, etc., are put into a special holding area so we can undo those changes to bring the database back into a state where it's ready to receive the next log backup. It's loosely coupled system. They're not tightly coupled. There's no automation in terms of failover, etc., but it does give you access to the data, and it's an enhancement on top of backup. You could roll all this yourself, but it's a lot nicer to have it packaged and set up for you. Database mirroring then is another advancement along the pathway here. So you have here, it's much like log shipping, except here what we're doing is the database 1 is sending its log stream, the stream of logs, both to the transaction log and across to the secondaries. So you have a pair of replicas, a pair of databases, and we're continuously streaming the transaction log data across. So instead of doing discrete log backups from time to time, you're streaming that data across from node to node in real time. That data flow can be synchronous or async, and what that means is for either one, when we're processing updates and writing log records to the transaction log within the primary, the DB1 here, we will write the records to the local transaction log at the same time that we write them over the wire to the remote transaction log. With a synchronous, we won't complete a commit, acknowledge a commit to the application until we've received acknowledgement from all the synchronous secondaries that they have hardened that data in their transaction logs. So in that way we can guarantee that no committed transaction on the primary will be lost on the secondary. It may not be immediately available because the secondary then has to reapply that change and replay that transaction, but you know you're not going to lose it at that point. Obviously, there's overhead in doing that round trip. So for that reason, we also have asynchronous option, and that's the case where we will do the same operation in terms of sending the data locally to the transaction log and remotely. We just won't wait for acknowledgement before we move on. So as long as there's no interruption of the network or in the secondary, that data is all caught and kept up. It just, there's a small window of vulnerability there. And you have a witness server that enables you to move the roles. So in full safety mode, which is the synchronous replication mode, with a witness server, you can have an automatic failover transition of roles from primary to secondary, secondary to primary. So it's a significant enhancement over what we had with log shipping. There's still some rough edges, but it's, like I said, big change. It's a new transaction data transport. So we have that new transport for moving data from node to node. It's not a bunch of separate jobs. It's all integrated into the engine, all controlled by the engine. It's a per database pairing. So you set up database mirroring between one database on server A with the same database on server B. Independently, you may set up the same relationship between two other databases, but there's no guarantee that the primary role will be in the same node. They may be opposite. And in full safety mode with a witness, automatic failovers are possible. And there's special connection strings you can construct, which says your connection target is node A, but your failover partner is node B. And what the SQL client does with that is it tries to make a connection with node A. If for any reason node A can't complete that connection, it will then go back and try and make the same connection to node B, assuming that a failover may have happened. So the connection string embeds in it, this is the node I expect to be primary, and we'll always try that node first. But if that's not available, we'll make the connection to the secondary. Finally, we have always-on availability groups. So always-on availability groups are built within the substrate of a cluster manager. So in Windows, it's going to be Windows Failover Cluster. In Linux, it's going to be Pacemaker, Service Guard, some other system like that. That's the system that maintains quorum and makes the decisions of when do you failover and where do you failover to. And in some cases, it may actually move resources like IP addresses around to facilitate things. So you have a number of nodes. Each node has one or more instances on it. So you have set up an availability group that spans those nodes all within the same Windows Failover cluster. And then the availability group is a set of databases, and that's the group part. So the idea is you have a set of databases that need to be running on the same primary. Typically, you have a situation where an application or more than one application need to reference more than one database in order to operate correctly. If one of those databases failed over to another machine, then the application would break. And that was one of the weaknesses of database mirroring. With availability groups, where you have that grouping of databases, they move as a unit. So if you're going to do a failover from node 1 to node 2, all three databases are then primary on node 2. And your application has access to all of those. So there's also a concept of a listener, and that is a floating IP address that moves with the primary node. It has its own IP address and name. That way you can have applications that are written to just connect to that name as if it were a singleton server out there, but in reality the server that's active will move from node to node as there's a failure, or you can use this as a mechanism to do rolling upgrades. So in this case, the primary is on node 1. You could upgrade node 5 and then node 4, and then node 3, then node 2, because nodes can run at a higher version of SQL as long as they're secondary, because they understand the older formats of the data. Some of the new functionality may not be available in that mode. And then you fail over from primary to node 2. At that point, the primary replica is running on node that has the higher version of SQL, so all the database structures get updated, and that gets fanned out to all the replicas. Meanwhile, node 1 is getting updated to the new version, and at the end of that, you have everybody running on the new version at the new level. So that's a way to do even a major version upgrade, and the downtime is limited to the amount of time it takes to do one failover, or 2 if you want to fail back. That's optional. So, automatic recovery of corrupted pages. This is a pretty cool feature here, where if one of the replicas application is running, it happens to read a page and finds that checksum doesn't match, so the page had gotten corrupted on disk. Instead of just going, out of luck, what it will do is query another replica for that same page. The other replica will respond and send that page across the wire to it. Presumably that's going to be a clean copy. The original then replaces the corrupted copy of the page on disk with the clean copy and completes the original read operation. The application doesn't really notice anything other than that read took a little bit longer than usual. There's no interruption to operations, and it's self-healing, which is a really cool concept there. Distributed availability groups. It's an interesting concept here. We have an availability group facility whose members are other availability groups. It's loosely coupled in that there's no common cluster across a distributed availability group. You might, but it's not a requirement. In fact, there are motivations why you wouldn't do that, and we'll get into that. It's really good for high latency multi-site configurations. So, for example, we had one customer who had a system that was running availability groups for their infrastructure and to replicate data between their sites, and they had sites spanning the North American continent. So that worked well for them. I mean, they had local access to the data for read, and the writes were routed to wherever the primary was running, and their application was about 80 to 90% read access, so that worked really well. What was a little bit problematic, though, I'll show in some slides here. So this is a diagram of a multi-site stretch cluster. So these two sites are significant distance apart. So it's not only latency, but it's also a lot of network hardware in between. So you have your primary and secondary on your primary site, and the secondary site has a couple secondaries. So the primary replicates data to the local secondary and to each of the remote secondaries. So you're sending the data twice over the wide area network link. Okay, that all works. It works fine. When it becomes a challenge is if there's any network hiccup between the sites. A lot of times the DR site cluster will decide that it's lost quorum, and so it'll take the secondary site off, even when all 4 nodes were up and running, because the primary site had the primary role. The DR site would get taken offline because it had lost quorum, and that may interrupt unrelated applications and generally cause problems. So what we've done is created distributed availability groups. There's no requirement that the entire scope of the distributed availability group be within one cluster. Each member availability group exists within a single cluster. So here, AG1 is the primary within the distributed AG, and it replicates data from its primary to its secondary. It also replicates its data from its primary to the secondary AG. So it thinks of this as just an opaque, that's the secondary AG. Within the secondary AG, the node that would have been primary if it was by itself, we now have a role called forwarder. So it accepts changes only from the distributed AG primary. You can't do ad hoc updates into that node, the forwarder on AG2. but then it replicates to its secondaries. One of the nice side effects of that is that you're only copying the data across the wide area link once. So you do one update from AG1 to AG2, and then it updates to its secondaries. Without the requirement of a single cluster underneath all of these, that means that you're insulated from the quorum issues you get if you have network dropouts. So that makes the system that much more robust. It's intended as a either read scale out or disaster recovery solution. There's no automatic failover here because, again, you don't have the common cluster infrastructure. And you can actually daisy chain these. I know of one customer that has a global presence, and so they have a daisy chain of distributed availability groups, one distributed AG that has a daisy chain of availability groups. So AG2 would replicate to AG3 and AG3 to AG4, etc. Reads are routed to whichever is closest from a network standpoint, and then writes get sent back to the primary, AG1. So that's one topology that you could have there. So that's a brief tour of distributed availability groups. There are some challenges, especially if you run in async mode, because you have to, instead of having the cluster determine that, okay, you're in sync, so it's safe, you have to do that determination of the LSN match, is it safe to move over from node A to node B. The command for that is force failover with allow data loss. It doesn't mean you're going to have data loss. It means that's a flag for you to think it through really carefully to make sure that you've got everything, that you've double checked that the LSNs on both sides match and that it's safe to proceed with the failover, or that you're okay with losing however many transactions it is. Direct seeding is another new feature within availability groups, which is pretty cool. What we're used to when you're adding a secondary to an availability group is you do a backup on the primary, either to local disk and copy it across, or to some neutral network share that both nodes have access to. So in this case, you're doing a backup to some backup share on my server. And then the secondary, you do a restore with no recovery, and then you can add that into the availability group. What we've done instead with direct seeding is allowed the primary to do a backup, and instead of writing out to a file, it uses the same log transport that we have set up for the availability group to ship the backup across to the secondary, and the secondary is going to then do a restore into its area and seed the new database. So if you're adding a database into an existing availability group, or setting up a new availability group, either way, this is a way to do it, allowing SQL to take care of all the work of making the initial copy of the database on the secondary node. So it's just very much easier, and you've got a very efficient log transport, or the transport between node A and node B to ship that data across. Required secondaries to commit. It specifies how many replicas must be in a synchronized state to commit transactions. So this is a case where you have a number of synchronous replicas, and normally if you don't have one, if one is down, we'll go ahead and complete the transactions, thinking that the highest priority is to keep your application online and running. And so there are cases where you can lose a replica and get into a state where the primary is taking transactions, and then the one synchronous replica that it had is completely blown up, and the second one wasn't quite up to date, and then you've lost data. So it's an way of making absolutely sure you will not lose any transaction. In this, we will not complete a transaction unless the number specified by this parameter, required synchronized secondaries to commit, have actually acknowledged getting the update. If it's not met, no transactions can complete. So for that reason, one of the engineers has dubbed this the anti-availability feature. But again, it's the strongest guarantee of no data loss. And this demand for this initially came from an organization which was processing huge amounts of retail sales. And if they ever lost one transaction, that's revenue that was lost, and they couldn't tolerate that. It would be better for them to have the customer's transaction fail and have to retry it than to let the transaction succeed and take the risk that that transaction may go away and not recognize that revenue. So it's, again, a way to be absolutely sure that your transaction will be recognized, will be protected by at least n secondaries. So you set it up to however many you want. But if you set it up to 3 or 4, if you don't have all 4 secondary replicas up and running, you won't do any work. So that's the other side of this. So we've gone in the progression from backup to log shipping to database mirroring to availability groups, and talked about some of the facets of availability groups. And the other major HA technology is failover clustering. So in failover clustering, you have multiple nodes, each with an instance on it, that share access to some form of shared storage. Either it can be multiple disks literally wired to each other, so you have physically attached storage. More commonly, it would be a volume within a SAN, which both physical nodes had access to. You can also do this where you have some kind of storage replication between sites. So for decades, SANs have had the ability to do replication between sites. There's also technologies built into operating systems or storage subsystems which will allow that replication to happen. But the idea is that all of the SQL instance data files, including master, MSDB, model, all the system databases, as well as all the user databases, reside on that shared storage. So a failover means taking down the instance that's running on node 1, and it's only running on node 1, attaching the storage, making it writable on node 2, and then bringing up the instance on node 2, because then it has access to the same data. And it's a very robust way of doing that. The failover will be slower than an always-on availability group, because you're not just starting the database, running recovery on the database, you're starting the whole instance up. But again, it's a different way of doing that kind of HA. Failover cluster storage options, file shares, premium file share in an Azure VM. Storage Spaces Direct is a Windows failover clustering technology that does replicated storage. Within Azure VM world, you have Azure Shared Disk, which was just recently announced. That allows you to have an Azure storage attached to your VM, which is shared with another VM. And as far as SQL is concerned, running on the VM, it looks just like it's physically shared. So SQL Server failover cluster instance with premium file share. It's a file share access, and for a long time we've been able to have your databases sitting on a file share. Ease of management, it's a very simple thing to set up. File shares are fully managed by Azure. This is obviously if you're running in Azure VMs. Premium file shares lower the work on your virtual machines. So your virtual machines don't have to manage the storage as well as everything else. The file share is managed on its own. You can have burstable input or output capacity, so you can burst that output to take care of spikes. Zonal redundancy is a concept where even within a data center, we split them up into zones, and zones are failure domains and update domains. So you're going to make sure that no two replicas within the premium file share are taken down for update of the hardware at the same time, nor are they using common power supplies or networking backbones. So you have a lot of redundancy even within the same data center that way. There's a link here to step-by-step tutorial to configure SQL Server FCI on premium file shares. Pros, you have fully managed file storage up to 100 terabytes, burstable performance. You can use AD accounts and private links. Cons, you don't get the Azure Blob caching, so that's a little bit less performance that way. It's a slightly lower IOPS to size ratio compared to disks. So with Azure storage disks, if they're directly attached, there's a ratio of IOPS to the size of the disk that we give you. With premium file shares, that's a lower number. SQL Server Failover Cluster with storage spaces direct. So here you have separate storage, so each VM has its own dedicated storage that's local to it, either local within the VM or local area. And storage spaces direct is Windows operating system level replication between those two. And it presents a clustered volume, and whichever node happens to be primary is the one you can update. So you, on top of storage spaces direct, you have the failover cluster and then a SQL failover cluster instance. So the SSD volume will be available to the VM that has the FCI on the primary. And here you can see some of the relationships between the different SSD sizes, the maximum size in gigabytes, the IOPS per disk, throughput per disk. So the P4 end, you have up to 32 gigabytes on the disk, 120 IOPS and 25 megabytes per second. P20, kind of mid-range, you have 512 gigs, 2300 IOPS and 150 megabytes per second, all the way up to P70 where you have 16 terabytes, 18,000 IOPS and 750 megabytes per second. So the pros is it scales to VM max for IOPS and throughput. So the VM has its own max for IOPS, and this solution will scale up to that max. You can leverage Azure Blob Cache for premium disks, so that speeds up your especially read access. Cons, it's limited to Windows Server 2016 or above only, and it requires high maintenance mode. It's not high maintenance work on your part. SQL Server Failover Cluster instance with Azure Shared Disk. It enables lift and shift deployments. So it literally looks just like an on-premise failover cluster with physically shared media. It's built for Windows Server, SQL Server 2008 and above. And leverages the failover cluster for disk arbitration. So the failover cluster will take care of moving the disk to whichever node has the primary role. Supports disk or cloud or file share witness. So you can set up your witness as an Azure file share and and that's virtually free. It's extremely cheap because you're not doing any I/O to it. There's very little cost there. Or you can have a disk that is also shared, or you can have a file share someplace. So with Azure Shared Disk, it behaves like physically shared disks on premise. It's available as premium shared disk in all regions. Ultra disks are extremely high performance disks, and they are at this point available in select regions. I'm not going to quote which regions because it's a moving target as they roll things out, but you'll have to look for which regions have Ultra disks enabled at this point in time. Premium is, again, available across all regions. There's no Azure Blob Cache for premium disks, but you do have that caching for the Ultra disks. shared disks are not replicated. So this isn't a case where each replica has a full copy of the data and we're just doing replication under the covers. It's one copy of the data. And so that does become a point of failure for you. And you may want to consider that in looking at the overall configuration you have. Azure Failover Cluster instances should use availability sets to maximize uptime. So availability sets are, again, making sure that no two elements in the set are in the same failure or update domains. So you make sure you don't both get taken down by the same maintenance operation. Proximity placement groups are a different slice of grouping Azure resources, and that makes sure that all the elements within the proximity placement group are within a very low latency distance to each other. So within a region, we have multiple data centers. Giving a proximity placement group means that all the elements are guaranteed to land in the same data center, and within that data center as close as we can get them, respecting the availability set restriction to not be in the same failure domain. Distributed network names is a different way of doing the floating IP address. It's facilitated by Windows Failover Cluster, so it's a Windows-only feature. What this does is means that you don't have to configure an Azure load balancer in front of your cluster to deal with moving the network name between the Azure VMs. With a distributed network name, you can have one DNN. Your listener is configured with a DNN instead of the virtual network name, which was the older technology. The traditional listeners are using a virtual network name. With a distributed network name, you can use that without having to configure an Azure load balancer. So it makes it much simpler. And it also speeds up failure and failover times, failure detection and failover times. So there's a few benefits to that. In on-premise, it's a perfectly valid solution, but you don't have nearly as many advantages to the configuration. Finally, a comment on Linux versus Windows HA. It's largely the same. It's the same features. It's the same SQL Server. It's all the same code base. There are some platform distinctions where Windows uses Windows Server Failover Cluster, Linux uses Pacemaker, Service Guard, or other clusters, and those clusters behave slightly differently, so you'll have some different characteristics. At this point in time, most of the Linux clustering uses a method called stoneth, which means if a node is not reachable, it's not responsive, we will crash the node in order to do as part of the failover. That is changing on the Linux side as things get better. But by and large, all of these techniques for HA and DR are applicable regardless of the OS you're running in. There's third-party products like DH2i is one that I've worked with that can help bridge the gap. They provide some interesting capabilities. They provide some tunneling access as well as an alternate way of doing quorum management. Containers and Azure Committed Kubernetes Services is another HA there are other whole talks just on that, and obviously those containers are running Linux at this time, so that's another distinction between Windows and Linux. So now we're going to move briefly into a discussion of what to use, when, and where. So what scenarios would you choose which solution for? So we're going to run through some scenarios here and talk about what to use there. So the scenario here, you have one single site, so there's no secondary sites here. You need basic disaster recovery. So in case hardware all goes down, you need a way to come back. There's not a stringent availability requirement, which means that if it takes a while to get things back up and running, that's okay. And it's a situation where cost is a significant concern. We'd all like to believe that cost is never a concern, but in reality it really is. It's always part of the equation. So a solution there would be backup restore, right? You don't need a cluster. It supports Windows and Linux. It's a very simple solution, and it achieves those scenarios. There's no reason to invest in a more complete, more complicated and costly solution than what is needed to meet your business requirements. Another scenario, the secondary server is a lower tier than the primary. So you have a primary that's really beefy, it's ready to do all of its normal job, and then you've got a secondary server that's there for emergencies, but it's really not as powerful as your primary. The recovery point and recovery time objectives are a little bit relaxed. They're not as stringent. You want no impact to the workload on the primary server. And your network may be poor or high latency, and you need support for standard edition. In this case, log shipping would be a good solution. There's no cluster required. Again, both Linux and Windows. It's not sensitive to network latency. There's very low additional workload on the primary server. It's just the backup data transfer, and it's supported by standard edition. Scenario, stringent uptime requirements. You have a need to scale out read access. The RPO is 0 and RTO is very low. You need fast and automatic failover, multiple databases that need to move as a unit, in which case the solution would be availability groups. So you need to scale out read access, so you have read scale with availability groups. That means that your secondary has access, read access. It's same behavior on both Linux and Windows. So it's a very good solution for this set of requirements. Another scenario, you have multiple sites, long distance and high latency. You need a fast recovery time objective in the event of an outage, and you may need to access your data at the remote site, in which case a distributed availability group meets the needs. So here you have one availability group in Los Angeles, another availability group in Boston. You have HA for long distance configurations. You have synchronous or disaster recovery between the two sites. You have read access in your remote site and high availability and resiliency within each site. Scenario, ISV solutions built with SQL Server on Windows. You have Linux certification happening in your enterprise. Enterprise is moving to an all Linux infrastructure. So this is a migration from Windows to Linux, but the same application is moving across. You have rigorous business requirements, and you need a seamless migration. So in this case, you can use a distributed availability group across platforms. There's nothing within the SQL data formats that is platform specific. We don't care. And so you can set up an availability group, a distributed availability group, from a Windows-based availability group into a Linux-based availability group. You could technically set up a single availability group across with a no cluster option, but typically this is a very smooth way of doing migrations between the platforms. Scenario, software as a service application, a website or such, catalog database with high volume of concurrent read-only transactions. You have bottlenecks on the primary due to read workloads and increased response time. So here you have, it looks sort of like a distributed availability group, but there's no failover. So this is just like all the log transport, keeping the secondaries going, but there's no guarantee of synchronization, and there's no failover capabilities. Any of the nodes can be Linux or Windows. It's purely for facilitating read access. It's a very low overhead solution, very simple. Brief note on Azure VMs versus on-premise. Azure VMs can be a good solution. You can choose VM variations to suit your specific needs. You can scale. Once you have your hardware in place, your VM in place, you can scale it up if your needs increase without replacing your hardware. There's no initial hardware cost. You do pay for the subscription over time. On-premise servers still give you the full control of your solution. You're responsible for availability, backups, etc., where in Azure VMs, a lot of that is taken care of for you. And you're obviously responsible for your own networking on-premise. So there are lots of options and tools to use. The big thing to remember from this whole talk is understand your business requirement, both business continuity and cost. They're both significant factors. Make a plan that meets those business requirements and then execute. That's how you're successful in this world. Thanks. Again, I'm Kevin Farlee. This is how you can contact me. Plug for joining a Microsoft focus group. Focus groups, you can engage directly with engineering and content teams to provide feedback. Highly encourage you to engage there. It's an opportunity to contact with us back in the engineering team. Love to talk to you. And evaluations help me get better. So thanks. I appreciate your time.